Today we're going to talk about section 6.5, which is called Operations with Radical Expressions. Okay, and we're actually going to take section 6.5 and break it apart into 3 different days. Okay, day number 1 here we're going to work on 2 things: simplifying radicals and then adding and subtracting radicals. Okay, we've been working a lot lately with simplifying radicals that are perfect squares, square roots, perfect cubes, cube roots, and so on. Okay, for example, we know the square root of 36 is 6. The square root of 49 is 7, and so on. Those are some perfect squares. We've also worked a lot with perfect cubes. The cube root of 27 is 3. The cube root of 64 is 4. Okay, and we even did a little bit with fourth roots. The fourth root of 81 is 3. And one thing that really helped us out with that was this little half a piece of paper that had the perfect cubes and fourths and fifths and things on it. Okay? The main focus of what we're going to work on, though, good news for us, excuse me, is we're mainly just going to work on the ones that are perfect squares. Okay, or not even perfect squares, but square roots as compared to cube roots and fourth roots and fifth roots. Okay? I think we've done this once upon a time too, but what about ones that are not perfect squares or cubes? And let's talk specifically just about perfect squares. Okay? For example, how about the square root of 24? Okay? 24 is not a perfect square. Okay? And kind of like with fractions, what we're going to want to do here with these is we want to reduce them or simplify them into a different form. Not a decimal, but a simple radical form. And I think we've done this once upon a time somewhere along the road. But what we're going to do is we're going to make factor trees. Okay? And one thing that's really going to be helpful with this, it's going to help you a lot, is to have your factor sheet handy. So if you have that, I'd maybe push pause here and get that. Or if you don't have it, I'd maybe push pause, go back to the resources at the beginning of the Google Classroom, and if you can, print that off, because it's going to be very helpful today when we simplify radicals. Okay? So if you need to do that, push pause, go ahead and do it, and then come back. Okay? All right, welcome back. Here we go. How does this work? So we know that 24, if you look at your factor sheet, there's a bunch of different factors on 24. A bunch of different numbers that multiply together to give you 24, but if you look carefully, there's one of them that's highlighted in black, and that's the 6 and the 4. And why are they highlighted in black? It's because the ones in black are the factors that are the biggest perfect squares, or one of the numbers is a perfect square, and it's the biggest perfect square. In this particular case, it's 4. And watch what I'm doing here. You notice the square root of 4 is 2. Notice how I exit off and I circle it. Then if I look at the square root of 6, the square root of 6 is not a perfect square either. Okay, it has some factors. The only ones are 3 and 2. But neither one of them are in black. So it doesn't simplify, it doesn't get me anywhere. We just leave it as the square root of 6. Okay, so my answer, the square root of 24, turns into 2 square roots of 6. And we're just going to practice just a couple other ones of these. But when we do your factor trees, and I'd kind of like to see your factor trees, okay, use your factor sheet. We're looking for the ones, the 2 factors that are highlighted in black. Okay, I'm going to do another one here. The one I'm looking for here is the square root of 32. Now once again, there's many different things that multiply together to give you 32. And there's a couple of them that are perfect squares. But if you look at your factor sheet, you notice the 2 that are highlighted in black are 16 and 2. And the reason 16 and 2 is because 16 is a perfect square, it's 4. And 2 is the dead end, so my answer is 4 square roots of 2. Okay? So again, if they're not perfect squares, we're going to use our factor sheets, we're going to break them apart and simplify them. Look for the ones in black. Okay? I'm going to do one last one here. 5 square roots of 48. Okay, now what's that 5? What's that 5 doing? The 5 is just a multiplier. Okay, we can kind of ignore it to start with. But if you look at 48, okay, and you go to its factors, you notice there are 2 of them highlighted in black on your factor sheet. It's 16 and 3. And the square root of 16 is 4. And I have a square root of 3. Okay, so now what do we do? Well, this is a big 4, and like I said, that 5 is just a multiplier. So I'm going to multiply 4 times 5 to get 20 square roots of 3. Okay, it's just a multiplier, that's all. Okay, but that's the types of things that we're looking for with these ones that are not perfect squares. is I want to see your factor trees. Show me your work. Okay? How about variables? Can variables be perfect squares or perfect cubes? Well, they sure can. We've worked with them before. Okay? What if I wanted to find the square root of x squared? Well, x squared is a perfect square. It's just x. Okay? How about the square root of x to the fourth? When we had a little 2 out here. I think x to the fourth was a perfect square also. Its square root was x squared. What if I went more? What if I had x to the sixth? And I wanted the square root of x to the sixth. Some of you are seeing a pattern here. It's x to the third. Okay? What did I do with the exponent and the little root out here in front? We divided them. Yeah. And if it divided evenly, then it was a perfect square. Like one more. What if I had the square root of x to the 10th? Well, 10 divided by 2 is 5. Okay? Does this little pattern work with cube roots and fourth roots? It sure does. What if I had the cube root of x to the 6th? Well, 6 divided by 3 is x squared. The fourth root of x to the 12th. 12 divided by 4 is x cubed. We just divide by whatever root it is. Okay? And I think most of the time what we've seen when we had those, they divided evenly. Okay? If it was a perfect square, divided by 2 evenly. A cube, it divided by 3 evenly. A fourth, it divided by 4 evenly. But down here at the bottom says, what if they're not perfect cubes or squares or fourths or whatever? Okay? What if I had this one? And I wanted the square root of x to the 5th. Now there's 2 ways you can think about this. If I back up here a second, I know that x squared is 2 of them. Every 2 x's make one big X. Every 2 square roots of x's turn into a big X. Okay? And one way to think about this is if I think of x to the 5th, it's 5 of them. 5 x's under the radical. Okay? Well, every 2 turn into a big X. That turns into a big X. And then there's one left over, and this is my remainder. Okay? And that little guy, he has to stay under the radical. So what this simplifies to is x squared with the square root of x. If you look at that closely. Okay, another way to think about it, and this is what some people do, is they just say, well, does 5 divide by 2 evenly? No. But how many times does 2 go into 5? 2 goes into 5 2 times, so I get an x squared. 2 times 2 is 4. What's my remainder? How many more to go to get to 5? 1. So there's x to the first left over as a radical. And as you get good at these, if you do the division, maybe it's a little bit shorter, but an awful lot of people like seeing the visual as well. Okay, let me do another one here. Okay, how about the square root of x to the 9th? Okay, well I can draw out 9 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9. These 2 turn into a big X. Those 2 turn into a big X, and a big X. Oh, there's only one left over. That guy's by himself under the radical. Well, how many X's do I have out front? I get x to the 4th with the square root of x left over. That's one way to think about it. Or, think of it this way. The square root, how many times does 2 go into 9? 2 goes into 9 4 times. So it's x to the 4th. Okay, and 4 times 2 is 8. Well, there's one left over. There's a remainder, x to the 1st. Okay, so it's not a big deal if they don't divide it evenly. Okay, it just has a remainder of 1 under the radical. Okay, so a little bit on simplifying radicals. If they're not perfect squares, do factor trees. If they're variables, we can divide them. Okay, whoops, hang on, one more thing. Okay, let's practice, put a couple of these together. What if I had 3 square roots of 12x cubed, y to the 4th, z to the 7th. Okay? And this big 3 is a multiplier. It's 3 times the square root. Okay? Well, let's treat the number parts and the variables separately. How about 12? Is 12 a perfect square? No. Okay? So I'm going to break it apart. I'm going to use my factor sheet, and I'm going to look at the ones in black are 4 and 3. The square root of 4 is 2. Okay? That number, the big 2, has to multiply any number out in front, and I end up with 6. 2 times 3 is 6. And then I have a square root of 3 left over. Okay, so that took care of the 12. And the big 3 out in front for that matter. How about x to the third? Okay, let's think. How many times does 2 go into 3? 2 goes into 3 one time. Okay, that's a 2. And there's a remainder. There's 1 left over to get to 3, so there's 1, or x to the first left over. How many times does 2 go into 4? Does 4 divide by 2 evenly? Yeah, it's 2. It's a big y squared with no remainder out in front there. And how about 7 divided by 2? Well, 2 goes into 7 3 times. So I have z to the third. And 2 times 3 is 6, well, I have a remainder of 1. That gets left under the radical. Okay? So we can do it with numbers, variables, and combinations of both of them. Okay? So that's simplifying radicals. Okay? Ultimately, we're going to put it together here. We're going to add and subtract radicals. Okay? And just like when you do fractions, okay, after we add and subtract fractions, you always hit a check to make sure your answer was simplified all the way. Okay, well, the same thing is going to be true when we add and subtract radicals. Our answer has to be in simplified radical form. Okay? Let's talk about this real quick. You guys know a lot about this. 3x plus 4x is 7x. Why can I add those together and get 7? Because these two things are like terms. And what makes them like terms is the variable. They both have an x, and it's also x to the first power. 3x plus 4x is 7x. What if I had 5a squared plus 3a squared? That's 8a squared. Again, the variables are the same, and they have the same power. Okay, both of those things have to match. If they do, I can add them together. And notice how that part stays the same. When I added these 3x plus 4x, it wasn't 7x squared. It just stays 7x. The variable part, the exponent part stays the same. Well, we can do the exact same thing with radicals. Watch this. 2 square roots of 5 plus 4 square roots of 5. Are those things like terms? Yes, they are. And what part of it is a like term? They both are square roots of 5s. Okay? And we're just going to count. Well, I have 2 square roots of 5 plus 4 square roots of 5. I get 6 square roots of 5. It's as simple as that. The radical part does not change. Just like the variable parts up here don't change. It stays square roots of 5, and we're just counting them. Okay? But the radical part has to be the same. Let's try a couple others here. 3 square roots of 2 plus 4 square roots of 2. While they're like terms, I get 7 square roots of 2. Does it work with subtraction? 8 square roots of 10 minus 3 square roots of 10 is 5 square roots of 10. The radical part is the same. Okay? Well, the last thing here, what if the radical part is not the same? Then what do we do? What if they're not like terms? Okay? What if I had 4 square roots of 3 plus 2 square roots of 12? Okay, now it doesn't look like they're the same. Here I have a square root of 3 and I have a square root of 12. Well, kind of like fractions, okay, we can sometimes do some reducing first or some simplifying first. Okay, let's look at the square root of 3. Is there anything I can do with the square root of 3? No, it's kind of stuck. So that's going to stay 4 square roots of 3. But the other radical, the 12, I can simplify. And if I look at my factor sheet and I break it apart, I can break it apart into 4 and 3, and the 4 turns into a 2. Just don't forget to multiply this 2 with that 2 out front, and I get 4 square roots of 3. Ha! Well, look at that. By golly, are they now the same radicals? They sure are. The coefficients happen to be the same also, but 4 square roots of 3 plus 4 square roots of 3 is 8 square roots of 3. Okay? And so even though it didn't look like they were able to be combined at the beginning, once I simplified it, it turned into 2 radicals that did have the same numbers underneath them. Okay? All right, we're going to practice just a couple others here real quick. How about this one? Negative 2 square roots of 3 plus 4 square roots of 27. Okay, now they don't look like they're the same either. I can't do anything with the square root of 3. That's kind of a dead end. But 27 has some factors. If I looked at my factor sheet, 9 times 3 are the two that are highlighted in black, and 9 turns into a 3. A lot of people forget to multiply it by the number in front. This turns into 12 square roots of 3 and negative 2 square roots of 3. Turns out they are the same. If I add them together, now I get 10 square roots of 3. Okay, and just so we're all crystal clear, I want to see a little bit of work. If it's not a perfect square, I want to see your factor trees and show me how they turn into the same like terms and then add them together. Okay? All right, I have two last ones we're going to try here. A little bit bigger ones. Excuse me. Okay. 3 square roots of 18 plus 5 square roots of 12 plus 2 square roots of 27. Can we add these three things together? Now right now it looks like all the radicals, all three of them are different. A square root of 18, a square root of 12, and a square root of 27. Well, let's try and simplify them. Again, using your factor sheet, there are many different ways to do 18, but the two that you want to use are the black ones, 9 times 2. That turns into a 3. The square root of 9 is 3. And this 3 times that 3 is 9 square roots of 2. Okay? The square root of 12, we can do 4 and 3. The square root of 4 is 2. 2 times 5 is 10 square roots of 3. And 27, if I did my factor sheet, is 9 and 3. The square root of 9 is 3. 3 times 2 is 6 square roots of 3. So I've just simplified each one individually. And now I'm going to look for like terms once all those radicals are simplified. And I think I see a couple of them right here. I see a couple square roots of 3's. 10 square root of 3 plus 6 square root of 3 is 16 square root of 3's. Okay, so I've kind of combined those two, and this is the only guy that's left. There aren't any other square roots of 2's for it to combine with, so you can do one of two things. You can add it at the beginning, 9 square roots of 2 plus that, or you could certainly add it at the end and have 16 square roots of 3 plus 9 square roots of 2. The order doesn't matter. There isn't any magic order to write these radicals in. Just make sure we have the correct signs on them, and we're all good to go. Okay? All right, I got one last problem. Here it is. It's kind of a big one. Negative square root of 27 minus 3 square roots of 45 minus the square root of 20 plus 2 square roots of 45. Okay, so it looks like there's a couple, and the couple 45s are the same, but the other two are different. Before we do any combining of those, let's just simplify each one of our radicals first. Okay, and a lot of these are getting to be repetitive. 27, we'll use 9 and 3, because 9, the square root of 9 is 3. And don't forget about the negative 1 out in front there. This one turns into negative 3 square roots of 3. 45, if you looked at your factor sheet, the two that are in black are 9 and 5. The square root of 9 is 3. And 3 times negative 3 is negative 9 square roots of 5. 20, we're going to use 5 and 4. And the square root of 4 is 2. And don't forget there's a negative number out there, so it's minus 2 square roots of 5. And back to 45 again, I'm going to use the same two I used over there, 9 and 5. The square root of 9 is 3. And 3 times 2 is positive 6 square roots of 5. Okay, so it's a little bit of work simplifying those. And again, I want to see that. And then go back and let's look at our like terms. I think I have several square roots of 5 there. Negative 9 minus 2 is negative 11. Negative 11 plus 6 is negative 5 square roots of 5. And then this guy just comes along, negative 3 square roots of 3. And there's my answer right there. And like I said, all these radicals that we've been doing all the time here have been square roots. And that's going to be our primary focus today. Okay? But once again, before we can add and subtract radicals, the radicals have to be the same. If they're not the same, show me some factor trees. And oftentimes, they're going to turn into radicals that are the same that you can combine. All right, thanks for tuning in.